Welcome to the chapter 3.4 lesson video. Today we're going to be talking about linear and angular speed. This is another topic where there's really just some formulas. And if you can learn the formulas and you learn what to plug in and how they kind of work and how to read the problems, it'll help you do well on this upcoming chapter test. All right, so let's go ahead and get started. Okay, so we can calculate linear and angular speed, and we'll talk about what the different things are and the different situations that you'll find them in. Okay, so linear speed is the actual speed. Now, when we think about actual speed, we're talking about like the object traveling, like we could say a car travels like 50 miles per hour. That's the actual speed. Linear speed is like the speed of the object, okay? So if you were to like pull out a radar gun and track its speed, that's linear speed. Linear speed is always expressed in units of distance per time. So units are going to be really important for this chapter, so making sure you do distance per time, feet per second, miles per hour, something like that. And so linear speed works like this. The linear speed of an object is the arc length, the distance it travels over time. Now, this S, we have a bunch of ways to express it, and you're going to see that we can kind of get some different forms of this equation. So just a little side note to yourself in case you want to make sure that you remember it. S equals R and theta. So as long as you know your radius of your circle and the angle in radians that it travels, you know what this S is. And then T is the time it takes for it to travel that distance. Now, linear speed is represented by this little V symbol that we're going to use here to symbolize linear speed, okay? So, here's our first example problem. It says a yo-yo has a 2-foot long string and is swung around so that it travels 31 pi over 4 radians in 2 seconds. I don't know if that's a realistic speed or anything, whatever, but we'll go ahead and we'll say that. So the first question says, find the distance that the yo-yo traveled. So the first thing we're going to do is we're going to find S. Now remember, S equals R theta, where theta has to be in radians. The theta they give us is in radians, so we're good. And then R is the radius of the string. So this should be a pretty straightforward calculation. So we're just going to say S equals 2 times 31 pi over 4. And we'll just do some pretty simple simplification, leaving us with a 2 right there. So it might not be the most friendly looking answer, but our arc length for this problem is 31 pi over 2 feet. Okay, because remember, arc length is a distance. Now that's some decimal. We don't really care exactly what it is at this point. We're going to leave it in that rather than abbreviating, changing it to a decimal or anything like that. So this is now our S. This is our S, okay? So then the next thing says, find the linear speed of the yo-yo. So if that yo-yo was hitting you, how fast would that yo-yo have been going? So our linear speed formula is this little V symbol equals S over T. Well, in the previous problem, we just found S. This is our S right here. We just found it in the previous problem. All we need to do now is divide it by the T, the time, and we'll get our answer. So we can write this in a number of different ways. I'm going to go ahead and write it as 31 pi over 2 divided by our time T, which is 2. Now, when we divide by 2, divided by 2 over 1, we multiply by the reciprocal. So this really becomes 31 pi over 2 times 1 over 2. So we get 31 pi over 4. And then our units here, this was feet. Remember, so we say feet per, and then the units of time was seconds. Now, that number right there doesn't mean a lot to you. If you got pulled over by a cop and they said you were going 31 pi over 4 feet per second, you would say that's a crazy sounding statement. So if we want to convert that into a more understandable answer, if we needed to, or if the problem asked for it, we would plug into our calculator and we would get 24.35 feet per second. Okay, so these are the same answers. One's just a decimal approximation. It doesn't matter what you give unless the directions say give exact answer. If the directions ask for an exact answer, you do this one. If it says give an approximation to decimals or something like that, you'd give this answer here. All right, so that's linear speed. So that's how fast the object is actually traveling. All right, our second type of problem is called angular speed. Angular speed is the amount the central angle has changed per a unit of time. So this is kind of the amount that the angle is changing, the amount that it is rotating over amount of time, how many degrees, how many radians or whatever it's going to go through. Now, I say degrees and radians. Realistically, when you're getting this theta, you're starting in radians. Your theta should always be in radians. If you wanted to convert it to degrees afterwards, that's totally fine. But the formula is pretty straightforward. It's this little W symbol, right? A little bit of a W shape. And it says theta over time. So you just take your radians measure, theta, and divide it by the time and simplify the fraction down. Whatever you get, that is your angular speed, how many degrees it would transpose through in that amount of time. All right, so there are 3 hands on an analog clock: the second hand, the minute hand, and the hour hand. And it says find the angular speed for each hand as a measure of radians per minute. All right, now let's talk about how we're going to do this problem. So in a minute, so let's talk about the hands on a clock first. That'll probably be a good idea. So we have a clock. There's 3 hands. There's the second hand, which goes around once per minute. There's the minute hand, which goes around once per hour. And then there's the hour hand, the shortest one, goes around once every 12 hours, right? Because there's 12 hours on a clock and then it repeats. So we're going to do this in terms of radians per minute. So the way we'll kind of generalize this is we're going to talk about one rotation, and then I mentioned it just a second ago, and we'll talk about how long it takes it to do that in terms of minutes, how many minutes it takes to do a full rotation. All right, so we'll start with the second hand. All right, so the second hand, it does one rotation. One rotation is 2 pi radians, and it does that one rotation every, how long does it take the second hand to go around? It takes 1 minute. The second hand goes around every 1 minute, so we do 2 pi divided by 1, so this is just 2 pi radians per minute. In other words, the second hand does a rotation every 1 minute. It does a full 2 pi every 1 minute, and it repeats and it repeats and it repeats. All right, now the minute hand is a little bit different. The minute hand, all right, the minute hand, it has to track a whole hour. There's 60 minutes an hour, that whole type of thing. So the 2 pi, it does a full rotation every how many minutes? It does a full rotation every 60 minutes. So if we simplify that down, we end up with pi over 30 radians per minute, right? Because it does a full rotation every 60 minutes. So that 2 pi, that whole circle, gets divided between those 60 minutes, meaning it does only 1/30th of a pi every single minute. So it does a smaller chunk, right? These are going to get smaller, right? Because these hands go slower as we go on. So then our last one is the hour hand. The hour hand, you got to remember a clock, it has 12 hours in a rotation. I know there's 24 hours in a day, but it does that twice a day. So it does a full circle every 12 hours, but in each of those 12 hours, there are 60 minutes. Right? So each of those 12 hours, there are 60 minutes. So if we simplify this fraction down right here, we could do a little math to help us out. We'll reduce that down to a 6. We have 6 times 60 on bottom now, so we get pi over 360 radians per minute. All right, so there we go. We found the angular speed for each of those hands on the clock. So remember our angular speed formula, the one we just used. What you're going to do is you're going to take the amount that it rotates and divide it by the time that it takes to rotate through it. And that's what we did on each of these. We took the whole circle that it rotates, divided by the number, because it says per minute, so divided by the number of minutes it takes to do that. All right, now this last one, there's a little extra problem on here. It says, now that you found the angular speed, and these are angular speeds right here for each of the hands, that's great, find the linear speed of a point on the tip of a second hand that is, it's covered up for me, that is 3 inches long. Okay, so we're going to go ahead and do this for a problem. So we're now going back to our other formula. Our other formula was the linear speed formula, and it says we needed to take the arc length and divide it by time. Well, I don't have the arc length right off the bat here, so I'm going to take my radius times theta, that's the formula for arc length, and divide it by time. Now, if you notice something right here, you might actually be able to kind of shorten this up a little bit, and this is a little helpful trick here. So S was r theta. That's how we got this top piece here. Well, theta over t is our angular speed. All right, so theta over t is our angular speed. And look, we have theta over t right here. So really another way we can write our linear speed formula here is to go r times the angular speed, right? Because this theta over t is the same as theta over t. And so if we just multiply r by whatever theta over t is equal to, which is our angular speed, we get the same thing. Well, we already found the angular speed for the second hand up over here. So if we want to know the linear speed here, all we have to do is multiply the radius, which we said was 3 inches, times the linear speed for the second hand, which was 2 pi. And it'll give us that the linear speed for this problem is 6 pi, and then our measurement is inches per minute, right? Because it does that 2 pi radians every minute, and then we multiplied it by the 3 inches, and so it gives us this formula. Well, now, once again, that doesn't mean a whole lot to the normal human brain. 6 pi is kind of an arbitrary thing. So if you wanted to convert that into a decimal, you would say it is 18.8 inches per minute. These are the same thing. It all depends on what the directions tell you, what they actually ask for when you're solving the problem. All right, let's keep going. So here is our formulas, and we kind of laying out all the formulas that we know here. There's actually kind of our earlier formulas on the bottom here as well. We have our angular speed formula. It is the angular speed, this little W shape, is the radians divided by time. So you just say how many radians it rotates through per time unit. And your units of measure on the end will always be radians per minute, radians per second, whatever the time unit you're dividing by is. Now, linear speed is a little bit different of a formula. It is this V symbol for linear speed. This is how fast the thing is actually going if it were to like run into you or something. Our traditional formula is this, the arc length over time, but we don't always give arc length. So what we can do instead is write arc length as r theta over time. Well, and if we see it in that way, we also know that theta over t, which we have over here, is the angular speed. So you can also write it as r times angular speed. So this one's really versatile. You can kind of do whichever method or whichever formula you want, depending on what information they give you. And this will always be a traditional speed, distance over time, meters per second, miles per hour, something like that. That is our linear speed units of measure right there. Make sure you guys are including your units of measure on every problem. That's going to be a big thing that I'm looking for on your quizzes and tests, and something that you will get marked down on, especially if you leave it. And then we have our two formulas from earlier, our arc length formula, we kind of talk about up here a little bit. The arc length S equals our radius times theta, and that's always a measure of distance. And then our area, that's like the shaded in region of one of those slices of pie, it's equal to 1/2 the radius squared times theta, and its units is distance squared. So like feet squared, meter squared, something like that. One really important thing to emphasize is all of our thetas in all 4 of these equations is in terms of radians. If you ever get a theta in terms of degrees, change it to radians, and then you can use these formulas. If you don't, you're going to get the wrong answer. So make sure you change it in terms of radians. That being said, I would make sure, take a moment, pause the video, write this down on a sticky note. Write these down somewhere really useful, somewhere really quick, where you can kind of access them as you're working on the study guide, as you're working on the homework, as you're reviewing stuff, something to keep by you, so that way you don't forget what these formulas are. And that's just kind of one thing that gets taken out of the difficulty of these problems. All right, so we got one last problem here, and this says a Ferris wheel has a radius of 40 feet. All right, so we already know what the R is. A person takes a seat, and then the wheel turns 3 pi over 4 radians in 45 seconds. We're going to draw a picture of this in just a second. It says find the linear and angular speed of that person on the Ferris wheel. If the wheel stops after 45 seconds, how high off the ground is that person? This is kind of a little bonus question, so we'll leave that one for just a second. So let's start by drawing a picture. That's probably going to be the most helpful thing. So I'm going to draw a circle right here, and I'm going to explain that when you get on a Ferris wheel, you get on at the bottom. If you think about Ferris wheels, if you've ever been on one or seen one, you get on at the bottom. So we're going to start our circle a little bit differently here. So there's where the person gets on. They're going to travel on the Ferris wheel for 3 pi over 4. All right, so 1/4, 2/4, 3 pi over 4, you're going to be up here in this quadrant right here. So this is our theta is 3 pi over 4. 3 pi over 4. Our radius was already given to us at the start. It is 40 feet. feet. And then the time, they give us the time as well. They say that took 45 seconds. So it's going pretty slow, 45 seconds to do that rotation right there. Okay, so it says find the linear and angular speed. Well, if we know the formulas, if we can write those down, this shouldn't be too bad. So we'll start with the linear speed. The linear speed is r theta over t. Since they didn't give us the arc length, they gave us the pieces to get arc length, r and theta. We're going to use that form of the formula. So we'll go r theta over t, so that'll be 40 times 3 pi over 4 divided by our time is 45. And we'll just calculate that out. So the 40 and the 4 we can simplify, make that just 10. The 45 and the 3, we can simplify that to be 15. And then the 10 and the 15, divide those both by 5. This will become a 2, and this will become a 3. So we end up with 2 pi over 3, and we're going to make sure we do the proper units of measure here. It was a distance, and our distance is in feet, and a time, and our time was in seconds. So 2 pi over 3 feet per second. I'm just going to leave it like that. I know I can change it to a decimal if I want. It did not ask us for that, so I'm going to leave that be. And then our other formula is our angular speed. That's the little w thing equals our theta, which is 3 pi over 4, divided by our time, which is 45 seconds. Now I'm going to rewrite this. I'm going to make that 45 over 1. I'm going to rewrite this as 3 pi over 4 times 1 over 45. And I'm going to simplify what I can. So the 45 and the 3 are both divisible by 3, so this become a 15. All right, so pi times 1 is pi. 4 times 15 is 60, so I get pi over 60, and then our units here is going to be radians, because that's our angle, per second. Awesome. All right, so here's our linear and angular speeds. We went ahead and plugged in to find those for this problem. Now, this second part of the problem asks us something interesting. It says, if the wheel stopped here, how high up is the person? And that might not intuitively be initially like making a ton of sense, but I'm going to try and draw a little more detailed of a picture here and see if it helps us figure it out. Let me erase something. I didn't quite draw it like I wanted. All right, so if I draw a little more of a circle here, so here's my circle. Well, to the center of the circle, we know this distance right here. This is just the radius of the circle. We know this distance to be 40 feet. All right, so we're using a little bit of logical reasoning here. So to the middle of the wheel is already 40 feet. If we look at our picture, we can see that it stopped up in this quadrant. Well, you're like, well, I don't know how much it stopped up, but they give us a denominator right here, right? We know that pi over 4 in terms of radians means that we can draw a triangle to up here where it stopped. And since it was pi over 4, we know this is a 45-degree angle. Okay, since that's a 45-degree angle, we know that we can find the other two sides. We just need something from this triangle. Well, this diagonal right here from the center of the circle to the edge is also 40 feet. If we know that the hypotenuse there is 40 feet, then the opposite side, we can use our 45, 45, 90 problem. Remember, 45, 45, 90, this is a root 2, a. So it has to be something that we can find. So since this is 40, we know that this piece right here is going to be a root 2 equals 40. We can solve for a, divide by the root 2, so a equals 40 over root 2. Rationalize your denominator. You're going to get that this piece right here is 20 root 2. Well, you now know that the person that we're talking about is 20 root 2 feet above the midline, and then the midline is 40 feet above the ground. If we add those two units together, we get 40 plus 20 root 2. You can't combine those together, unfortunately, because one of them has the root 2. And then we just add our units of measure, feet. So the person is 40 plus 20 root 2 feet off the ground. And as always, if you wanted to change that to a real world thing, if that mattered to you, you could go ahead and just plug it into your calculator, and you would get that it is equal to about 68.3 feet. Right? And you knew it was going to be less than 80 because 80 would be the top, 40 plus 40. So 68.3 seems fairly reasonable. All right, so that's a little bit challenging a question there on the end. Hopefully that's enough information for you to get started on the assignment. If you have any questions, please reach out to me. Otherwise, I'll see you in our next live session. Until then, I hope you have a great day.